Good evening. For this programme, we're going to talk about star deaths. But first of all, Chris Clinton and I have the usual news notes. I don't know whether you saw the eclipse of the moon on October 28. I didn't, did you?
No, I was clouded out in London, but we have had a few photos in from people who were luckier across the UK. For example, this one by Chris Proctor in Devon, showing the red colour of the moon at totality. And this from Jamie Cooper, who'd given up on observing because of cloud, and then looked out his window having woken up and managed to take this shot. And a final one from Pete Lawrence just down the road here in Salesey.
I know, he saw it and I didn't most of the time. Something else you can see in the sky now, clouds permitting, and that is the planetary conjunction. Jupiter and Venus, less than 1 degree apart on November 5, so for the next few mornings they'll be well placed. A good chance for photographers.
No astronomical significance at all, but rather beautiful.
Of course, remember now, the SMART probe is approaching the moon. It'll go into lunar orbit very shortly, and that's a revolutionary thing.
That's right. It was designed to test technologies, in particular its engine, an ion engine, which has now been the most successful of its type. But for me, the exciting thing is we're about to get the science back, and we've just had these first images of the moon from SMART's far-infrared camera.
I wonder what it's going to show us. And, of course, the planet Saturn is very much in the news, because, after all, Cassini-Huygens is now approaching Saturn, and on Christmas Day, Huygens is going to be released. But we have got now first pictures back from close range of Saturn's amazing moon, Titan.
That's right, the only moon in the solar system to have a significant atmosphere. And until now, this atmosphere stopped us seeing the surface. But Cassini flew just 1,000 kilometres above the clouds and sent back two kinds of images. The first, by looking at very specific wavelengths, windows into the atmosphere, we get these shadowy pictures of the surface underneath. And the second type is to use radar. Fire radar down and see the reflections. It tells you about the nature of the surface. And the big question is it solid, is it icy, or is it watery, or rather liquid?
Well, we should soon know. Meanwhile, another interesting launch is due, SWIFT.
That's right, this is the NASA satellite, which is going to be the most efficient machine ever to detect gamma ray bursts, the biggest bangs since the big one, if you like.
Well, talking of big bangs, there was one way back in 1572 when a supernova burst out from the constellation Cassiopeia and was studied by the great Danish astronomer Tycho Brahe. And very interesting results this month, because the companion star has been discovered.
That's right, but of course it's no longer in the location where the supernova went off, because the explosion gave it such a kick, it's now been called a runaway star. It's moving rapidly through space and rapidly across the sky as well.
Well, a supernova does involve the death of a star. And that, of course, Chris, brings us on to our main theme this evening, star deaths. Now remember, stars are long-lived things, and these ordinary stars are. Our Earth, we know, is 4,500 million years old, and our sun's older than that. And the sun is a normal star, slightly unusual in that it's a single star, and most stars are members of pairs or binary system. Otherwise the sun is pretty normal. It's a long-lived thing. But remember, stars are very different in size and in mass. Have huge red stars like Betelgeuse and Orion, and tiny ones called white dwarfs. And stars die in different ways. They go through various stages in their evolution. This stage I'm delighted to welcome Professor Evans and Dr. John Pollacco. And I think first of all, let's talk about planetary nebulae. Now these are interesting things, they are lovely, and they represent dying stars. And some of them are easy to see with small telescopes. There's one called the Ring Nebula, the constellation of the Harp. That's very easy to find with even a tiny telescope. Of course, the name is misleading, given by William Herschel. He thought these things looked like planets. Well, of course, they've nothing whatever to do with planets, so they're not really nebulae either. But they certainly do represent a late stage in a star's evolution.
That's right, Patrick. They represent the dying stages of a star when they're evolving from red giant stars to become white dwarfs. And the timescale of evolution is actually very short. It's only about 50,000 years. So we're seeing a very short part in the life of a star.
Because a star shines not because it's burning, but because of nuclear reactions going on inside it, and it uses hydrogen as its main fuel, isn't it?
That's right.
And things start to happen when the hydrogen runs out.
That's right. When the hydrogen runs out, the star has to completely rearrange its internal structure, and eventually we end up in a situation where the envelope of the star has been ejected, and the core of the star is contracting. And during that process, the core gets very, very hot and illuminates the old ejected material.
Some of them can be bizarre. The Ring Nebula is a regular one, but there are others that are not.
Well, most planetary nebulae are in fact not round at all. Very few of them are round. Normal stellar evolution for a single star is difficult to make any other shape apart from a round nebula. So we have to invoke some other kinds of models to produce these beautifully butterfly-shaped objects. Even something like the Ring Nebula, M57, is not very round when you look at it in detail.
No.
So if you look at some of the other objects, NGC 2346 is very much a bipolar object. There are other objects.
The dumbbell, for example.
The dumbbell is very much an extreme bipolar shaped object.
The Helix Nebula.
The Helix looks more like the Ring Nebula in Lyra, and what we need is a model that can account for all these different shapes. And in fact, that model has evolved over many years, and if you can imagine that we're dealing now with a tube, in the case of the Ring Nebula, the tube is presented pole-on to us. So we're looking down the tube. In the case of a bipolar nebula, we're looking in cross-section through the tube.
What does this tell you about stellar evolution in general?
It tells us that we're missing something important. In fact, the most likely explanations for these shapes is probably either magnetic fields or the fact that we're dealing with binary systems. If we take the case of the binary to start with, composed of a small white dwarf and a star that is growing larger. As the binary system evolves, the gravitational attraction of the white dwarf causes material to be sucked off and deposited on the white dwarf and the star's orbit within the common envelope. Eventually the envelope is ejected and the white dwarf's wind causes the material to be blown out in bubbles either side of the equatorial plane of the binary, forming a bipolar nebula. This object here goes by the name of NGC 2346, is actually a binary central star. And here you can see the bubbles have been blown out of the equatorial plane.
When you look at a planetary nebula through a telescope, even a big one, you won't see the colours. I remember seeing the Ring Nebula, one of our best planetaries, through the Isaac Newton telescope in La Palma, one of our biggest telescopes. And there's no colour there. But these colours brought out in photographs, they do mean something.
They certainly do. As you say, when you look at a nebula visually through a telescope, the brightness is so low that they don't activate your colour vision. But when you see the colour photographs, the colours actually represent different elements that are present in the nebula. So for example, green is characteristic of oxygen, red is usually characteristic of hydrogen. So it tells you something about what elements are present in the nebula.
And these planetary nebulae, they gradually disperse, and what happens then?
Well, as time moves on, the nebula becomes fainter and fainter as it expands until we're left in a situation where all we see is a faint binary system.
And of course, there's a link here with novae, and another misnomer. A nova is not a new star at all, it's the explosion of a formerly faint star.
That's right, and these occur in binary systems where we have a white dwarf star in a binary orbit with a star like the Sun. And the gravity of the white dwarf star is so strong that it raises tides on the Sun-like star, drags material off, and this material then builds up on the surface of the white dwarf star. And eventually it detonates in a thermonuclear explosion. The kind of reaction that is currently occurring in the core of the Sun occurs on the surface of the white dwarf. And of course there's nothing to hold it in, and so we have an explosion.
And it doesn't last for very long?
It certainly doesn't. The explosion itself lasts for perhaps 2 or 3 years. The white dwarf is very hot after the explosion, maybe for about 20 or 30 years. And the remnant that's thrown off is sculpted in shape in much the same way as planetary nebulae are shaped.
And naked eye novae haven't been too uncommon, even in our galaxy.
No, that's right. The most recent bright nova was Nova Velorum in 1999. Then, of course, we had Nova Cygni in 1992, and another Nova Cygni in 1975, which, of course, you were co-discoverer.
I was a co-discoverer. I think I was 94th on the list. Certainly was there. But there are some stars which show more than one nova outburst. These called things recurrent novae. One, for example, the Blaze star, T Coronae, which flared up in 1866 and again in 1945. And again, they don't destroy themselves.
No, they certainly don't. And in fact, all novae are recurrent. The only difference is that the so-called classical novae have eruptions every few thousands of years, whereas the recurrent novae have eruptions on a human timescale within a few decades. And as you say, T. Corona Borealis is a prime example, as is Ares Ophiuchi, which is due for another outburst. And what happens here is that the basic reason for the eruption is the same. We have an explosion on the surface of a white dwarf star. But in the case of recurrent novae, there's quite a range of companion stars, including red giant stars in some cases, and stars like the Sun in others.
After all, a nova doesn't destroy itself. It goes back. You can have violent outbursts where stars do destroy themselves, and this is what we call supernovae.
That's right. And in the case of a supernova, what happens is that the core of the star collapses, and as a result, the star itself disintegrates and is dispersed violently into the surrounding space. And the core of the star then collapses into either a neutron star or a black hole.
Of course, we don't know when supernovae are going to appear, or in which stars they're going to appear, but we do have one or two cases of progenitor stars, stars we know about before they became supernova. And of course, that's the case of the 1987 outburst in the large star. We know what star it was.
Yes, one of the great things about that particular supernova was that the Large Magellanic Cloud had been surveyed several times photographically. So after the supernova event went off, we could actually determine something about the progenitor star. And the big surprise at the time was that it wasn't a red giant like stellar evolution had always predicted. It was a blue supergiant.
Could be when the next supernova will occur, we don't know. There are one or two stars in our galaxy, though, that are pretty good candidates. Rho Cassiopeia.
Rho Cassiopeia is a hypergiant, very unstable star, and sooner or later it will go bang, there's no doubt about that.
And in the southern hemisphere, the famous Eta Carinae, which 150 years ago was among the brightest stars in the sky.
That's right, and it's still intensively studied, and it's still very, very bright in the infrared. And like Rho Cas, it is one of the prime candidates for a nearby supernova.
Well, let's hope they aren't too nearby, because a supernova within a few light years of us would be pretty disastrous.
It certainly would, yes. If it was very close, then it would spell disaster for all life on Earth, of course.
But luckily, so far as we know, there are no nearby stars that are liable to go off that way.
Well, I think we have to be a little bit careful here, because supernova can also occur in binary systems. So far we've talked about supernova in massive stars, but you can have an occurrence whereby you transfer a lot of material, similar to a nova, onto a white dwarf. And if you transfer material at a very high rate, that star can also become unstable and cause the collapse of the white dwarf.
Of course, I don't remember, 1901, there was a bright nova, not a supernova, a bright nova in the northern hemisphere, and that has left a nebula, hasn't it?
It certainly has, and whereas in most nova explosions the nebula disperses fairly quickly, in the case of Nova Persei 1901, the nebula is still there, but we now also know that the nova is at the centre of a very large and extensive planetary nebula.
Because most stages of evolution are slow, but some are not, and there's some weird things around. I think of two particularly, a thing with the cumbersome name of V838. What exactly is that?
Yes, V838 Monocerotis was discovered in 2002 by an amateur astronomer in Australia, and it was reported as a nova, but early observations showed that it clearly wasn't a nova. And it turns out to be one of the most bizarre stars we've ever seen. It turns out to be an extremely cool star.
How cool?
It's around about 1,000 degrees. Very, very cool. And it has, there was material coming away from it in the early phases, but we now know that there's material falling back onto it. But it has associated with it a very bizarre and very spectacular light echo. When the star brightened, the light spread outwards and reflected off sheets of dust, and we see this as a light echo or an optical reverberation. It's exactly the same kind of phenomenon as you see with a sound echo, where the sound propagates outwards and reflects off buildings and mountains and so on.
How far away is it?
I wish I could tell you, but it's possibly around about 25,000 light years.
And what about the brightness? I mean, can an amateur telescope show it?
It was very bright in the early phase of its evolution, but it's now extremely faint in the optical, not because it's actually has low luminosity, but because it is such a cool object. It's very, very red. So it's very, very bright in the red and the infrared, but very, very faint in the optical.
Well, that's certainly a strange thing, but there are others. Remember some 30 years ago, the Japanese astronomer named Sakurai discovered a really weird thing, which we now call Sakurai's object. What exactly is that?
Yeah, this is stellar evolution before your very eyes, in fact. Most things take thousands of years to evolve. The Sakurai object is evolving at a timescale of a few years. 20 years ago, 15 years ago, this object was a white dwarf. But some white dwarfs can become unstable, and in the case of the Sakurai object, it reignited thermonuclear reactions and became a red giant again within a space of a few years. And during that time, we saw this star getting cooler and cooler. I think it was 1,000 degrees a month or a year. And we also saw the surface composition of this star changing, becoming more and more hydrogen deficient. And this corresponded to us looking deeper and deeper into the interior of the star. And in about 1999, the envelope of the star became detached and the star became very faint because the envelope became very dusty.
And what will happen to it eventually?
Well, it will go through another planetary nebula phase. This material, the photosphere, has now been ejected. The core of the star is warming up. We can see it warming up just. And the old envelope, which is now devoid of hydrogen, remember, will become illuminated by the star.
Let's talk for a minute, can we, about our own sun. It's a very ordinary star, except it's a single star. Well, that's been existing now for about 5,000 million years, older than the Earth, obviously. What exactly is going to happen?
Well, I don't think we really have to worry about this. We're probably about halfway through the lifetime of the sun, and in a few billion years' time, the sun will exhaust hydrogen in its core. It will become a red giant.
And of course, that won't do our Earth a great deal of good.
It certainly won't, and it won't do a great deal of good to anything that's on the Earth either.
Well, as we said, stars are long-lived things, and generally speaking, they take a long time to evolve. But they won't last forever. We know now our universe is roughly 13.7 thousand million years old. Is that old enough for any star to reach the dead center stage?
Well, we know that once a white dwarf is exposed and it starts to cool, and over time it gets cooler and cooler, and in fact the rate at which it cools is reasonably well known, and the coolest white dwarfs we can see give us a handle on how old the universe is. So we haven't got to the dead center stage yet.
But eventually, of course, we will. No star will live forever, which is a rather sobering thought, isn't it?
Certainly is.
Certainly is, but they will live a long time.
They will. Nye, Don, thank you very much.
Thank you.
It's nice to know we have a long way to go before the sun dies. And when I come back next month, we'll be talking about the world's largest telescopes. We'll be talking there to some of the people who've been using them. And Chris Lintott will be on his way to Chile. Until then, good night.
And there'll be an extended version of this episode of The Sky at Night on Monday on BBC 4 at 8:30.